Okay, so we're going to talk about exponential and logarithmic equations right now, which is topic 54. We're going to go ahead and solve exponential and log equations. These are, in fact, going to be, I would call them very basic logs and exponential equations, and we're going to be taking and kind of cherry picking certain problems of this. There are many different variations. There's many different options. We're going to look at specifically like 3 types of equations and show you how to solve these. These model exactly after what your practice is going to look like from delta math. So the first one we're going to look at is actually going to be the exponential equations. So the first type of equation we're going to look at solving it is a basic exponential equation. And the way we're going to be solving this is using this idea of if I can make the bases of an exponential equation match. So if I have some base b raised to an exponent of x, but then on the other side I have base b raised to a different exponent of y, well, what we can actually say is, well, since the bases are the same, I can simply just set the exponents equal to each other. So kind of looking at that in words, if 2 powers have the same base and they're equal, then what we can do is we can set the exponents equal as well. All right. So our goal here is going to be, we're going to have exponential equals exponential. Our goal is to change the bases to be the same. And then from there, we can just go ahead and just look only at the exponent level. Okay. So let's best start off with just an example. Here's a typical exponential equation. 32 to the x is equal to 2 to the 5th. All right. Now, the goal here is to make these bases be exactly the same. So what we're going to have to do is we're going to have to change one or both of the bases to be the same number. So in this particular case, though, I wonder if you're thinking, well, you know what? I really like this 2 that's listed there. And I really like the fact that it's raised to the 5th exponent. That really helps us out here. I would love to go ahead and turn 32 into a different base and have that be raised to the x exponent. Well, the question is, how can I make a 32 turn into a 2? Well, let's go over here to the margins and say, well, I know that 2 squared is equal to 4, 2 cubed is equal to 8, 2 to the 4th is equal to 16, and 2 to the 5th is actually equal to 32. So what we can do is we can go ahead and say, all right, I like this. We can rewrite 32 as 2 to the 5th, all raised to the x exponent. Now, some of you are freaking out already with the fact that there's like multiple exponents on top of each other. All right, calm down, first of all, calm down. All right. Do we all understand how we went and we changed that 32 into 2 raised to some exponent? We're all okay with that, yes? All right. So now what we need to do is we need to clean up this like double exponent that we got going on here, right? Well, if you remember back when we talked about properties of logs, right, when we were talking about log properties, we revisited the exponent rules that we had learned before, and I'm actually going to zoom in right here. Remember, whenever we had a power raised to a power, all we did was, or an exponent on top of another exponent, was we just multiplied them together, right? So going back to this problem, we can think about this as, oh, the equal sign's still there. We can re-envision this problem as such. We have 2 on the inside, right? Over here, it's really convenient. It's just raised to the 5th power. But here, what we're going to do is we are going to raise it to the 5 times the x that was originally there. So all we're going to do is we're going to take that 5 and multiply it by the x, which is already there, right? Well, hey, that's not so bad in this particular case. Well, what do we do now? Well, the property says, or the idea says, if I can get the bases to match, I can ignore the bases and just solve whatever's left in the exponent. So all I'm going to do here is I'm just going to look at the exponents only. Exponents only now. And if I'm looking at just the exponents, that equation says 5x is equal to 5. Well, that's an easy enough equation. What's the answer for this then? That just says x is equal to a 1. Right? And there we are. We can go ahead and solve exponential equations by getting the bases to match and then solving whatever equation is left in the exponent. All right? Questions on that? No questions from the chat. Okay. Let's go ahead and look then at the next one. All right, so here, if we're looking at the exponents, we have 27 and 9. What base could I turn 27 and 9 into? Any thoughts? Well, over here, when I was looking at 32, I was thinking like 2 raised to certain powers. Well, a lot of the time, we're either going to look at 2 raised to certain powers, 3, 4, 5, 6, 7, like basically single integers if we could. So in this particular case, if I showed you 9 and 27, what number maybe do they have in common here? Well, hopefully your brain is thinking, well, oh wait, I can rewrite this as 3 raised to the 3rd power over here, and 9 is really going to be 3 squared. Interesting. Well, that's really convenient, but we still have this like exponent on top of exponent idea happening here. So initially I wrote 27 as 3 cubed. Now all of that's being raised to the x plus 5. Now here I put my x plus 5 in parentheses because I don't want to miss out on any distributive property that may in fact occur. And then the same thing on the other side. I'm going to have 3 squared now for 9 is equal to, or raised to the x plus 2. Well, let's go ahead and clean this up just a little bit. We want to just have it be a single base of 3. So I'm going to go ahead and rewrite this as 3 and 3, right? We're allowed to do that. Well, what's going to be now in the exponent idea? Well, again, going back to our properties of exponents, we know that a power raised to a power, we just multiply the powers. So we're going to go ahead and write this as 3 and 2 times the original exponents, x plus 5 and x plus 2. Okay, any questions so far on that? Well, if the property says that I get the bases to match, I can mess with only the exponents. Well, we're going to go ahead and do that. There's no sense in dealing with this anymore. We're going to look at exponents only. Exponents only. So that means I have 3 times x plus 5 is equal to 2 times x plus 2. Wait a minute, isn't that just like an algebra 1 problem? Yeah, it's like chapter 3 in algebra 1. What are we going to have to do here on both sides? Well, hopefully we'll just distribute, giving us 3x plus 15 is equal to 2x plus 2. Yeah, from here it's just algebra 1 down. Well, let's go ahead and combine like terms here. So I'll subtract 2x from both sides, right? Giving us 1x is plus 15 is equal to 2. We'll go ahead and we will subtract 15 from both sides, right? Oh, that's going to be a 4 versus a 2. So subtracting 15 from both sides, it gives us x is equal to negative 11 is my answer. There we are. Okay, questions on that? All right, so if we go to this last example, let's take a look at this. Let's just be honest with each other in the sense of like 1,024, that's a really big number, all right? So kind of using our math off to the margin here, like we did over here, isn't necessarily going to be that as time efficient for us, right? So instead, what could maybe we utilize in order to go ahead and make our lives or this problem speed up a little bit in terms of the solving? Any thoughts on what we could use to maybe help us speed this up a little bit? Yeah, we're just going to use Desmos. Yeah, that's all we're going to use is we're going to use Desmos. I'm going to go ahead and pull Desmos up right now. So we can go ahead and see. Present a tab. Desmos. Here we go. So all we're going to do here is we have 16. Now 16, some of us, if I gave you 16, maybe some of us were thinking, I don't know, maybe 4 squared. Some of us are thinking 4 squared. So let's take 1024 and see if we can rewrite it as 4 raised to some exponent. So 4 to the third, well, that doesn't work. How about 4 to the fourth? No, 4 to the fifth. 4 to the fifth. So 4 to the fifth and 4 squared. Now, could you have done 2 if you really wanted to? Well, yeah, some of you may have said, well, wait a minute, I know 16 is 2 to the fourth. Well, yeah, we could have played around with that. We could have went 2 to the, we would have figured out that it was 2 to the 8th. Oh, nope, I lied. 2 to the 12th. 10th. There it is, right? So sometimes there's a combination of things that work, but let's go with 4 squared just to start, because I think the number is a little bit easier. 4 to the 5th, was it? And there we are. So we have 4 squared and 4 to the 5th. Okay. Now, since I have Desmos open just for a minute, we're going to make one little note at the bottom of this problem of something that may show up on Desmos. It shows up like 1 in every 10 problems. So maybe we'll see it, maybe we won't. Is how do we deal with negative exponents? And we'll talk about that here in a little bit. So we may come back and use Desmos for that. But for right now, 4 squared and 4 to the 5th is what we're going to be working on. So we'll go ahead and present a window. Back to the exponential problem. We had 4 squared and 4 to the 5th. 4 and 4, 4 squared and 4 to the 5th. And we still had our exponents here as x minus 4 and x minus 1. All right, well, just like before, we're going to go ahead and clean this up. It doesn't quite just say, we have a double exponent idea here, power to a power. So let's go ahead and rewrite that just to make our lives a lot easier and make this problem actually fit the property. So we're going to have 4 and 4. And in my exponents, then, we should note that we're going to have 2 and that 5, but they're going to be multiplied by whatever was originally there. So I have 4 to the 2 times x minus 4, and we have 4 to the 5 times x minus 1. So just like all these other problems, we're going to go ahead and solve this exponents only. Meaning that we have this equation of 2 times x minus 4 is equal to 5 times x minus 1. And just like before, this is just an Algebra 1 problem that we can make our Algebra 1 teachers proud. 2x minus 8 is equal to 5x minus 5, distributing correctly here. I would start off by subtracting 2x from both sides to go ahead and give us negative 8 is equal to 3x minus 5. We could go ahead and add 5 to both sides here. To the 5th, 2 squared. Going to go ahead and give us, let me clean that up a little bit. Giving us negative 3 is equal to 3x, so x is equal to negative 1. And we would actually solve from there, okay? All right, questions on those 3 types of problems? Now, we were going to make one general note down here about negative exponents. Negative exponents. It may or may not show up as we're looking at this. Negative exponents may or may not show up. So how do we deal with negative exponents? Well, remember, negative exponents either move numbers up or down within the fraction, right? From the numerator to denominator, denominator to numerator. More often than not, the ones we're going to see is going to be something like this. I may give you 1 over 49, right? Well, if I gave you 1 over 49, we could think about that as really 1 over 7 squared. And then if I wanted to get that 7 out of the denominator, we would have to write it as 7 to the negative 2. Okay? Now, why would we need to do that? Well, for instance, if I gave you the problem 1 over 49 raised to the x is equal to 7 to the 2x plus 1, in this particular problem, what we would have to do is we would say, oh, wait a minute, 1 over 49, I can rewrite that as 7 to the negative 2. And we're getting a little bit closer to having our bases to match. Do we okay with that? Yes? That may show up on yours. It's usually like 1 in every 10, but if it doesn't, then you're really lucky. But if it does, we know how to deal with it. Okay, you just make it a negative just to move it up. Okay, questions on that? Okay, so we're going to go ahead and move to the next section, which is actually we're going to pause and we're going to do a log method now. So the only log equations we're going to be doing are going to be two different variations. We're actually going to go ahead and actually go to the back side here to look at this graphic. Remember, we know how to move between exponential and logarithmic form. Yes, we know how to move between exponential and logarithmic form in the sense that the base is the base is the base is the base. So we had this idea of, well, I can just drop the base down, moving back and forth. And then we remember that the logarithm just equals whatever the exponent is. So our exponent kind of manipulated and moved around. And we had our answer was just whatever the argument was on the inside, right, as we're going through. So I wanted to show us this graphic. We talked about this before in our introduction to logarithms, how to convert logarithmic to exponential form. Now, on the back side here, we're going to go ahead and use this conversion pretty predominantly, all right? But I want to actually start off with this type of equation, which is a log equation, where, as you see, we're going to convert to exponential form. But the first thing that we're going to need to do is we're going to need to use our properties, i.e., we need to condense logarithms into a single logarithm by either multiplying or dividing. So when I say these properties, we're talking about what we did last class period, which was these three log properties, where if I'm if I'm multiplying two things in the argument, I can write it as addition, or if I see addition, I can write it as multiplication. If I'm dividing, I can write it as subtraction, or if I see subtraction, I can write it as division inside the argument. And finally, a log to a power rule. We're predominantly going to be using these two, and we're going to be condensing. So we're going to be moving from the right to the left. We're going to take multiple logs and write it as a single log. So let's go ahead and take a look at this first example. So we should note that we see two logs with the same base. We see log base 2 and log base 2. But in fact, the arguments are different. However, we should note that we are adding between here. And since we are adding, that is a giveaway that we can use the product rule. And remember, when I have the product rule, what that means is we can take and we can condense this into a single logarithm. Log base 2 of, I can take those arguments and multiply them together. 5x times 3. And conveniently, it's still equal to a 1 from the other side. Okay? Well, cleaning this up a little bit, we're able to write this as log base 2 of 15x, right, is equal to 1. Right? Well, note up here, we'd use our properties to write it as 1 log, and then now we're going to go ahead and convert. So now we're going to go ahead and we're going to do our convert to exponential. Convert. Convert to exponential form. Well, we just talked about this on the back, how we do our conversions. The base is the base is the base is the base, right? The argument becomes what we're equal to, and the exponent, the answer here, it becomes our exponent, right? Logs really equal exponents. We're going to go ahead and do this switcheroo here. So the base is the base is the base is the base. 2 raised to the first exponent is, in fact, going to be equal to 15x. So converting from log to exponential is what we're doing next. Okay, any questions on that? Well, luckily for us, this is just an algebra 1 problem that we can continue to simplify. 2 is equal to 15x. So that means x is equal to 2 over 15. Here's my answer. Okay. Questions on that? Well, in this next problem, you can see I've already started highlighting. We see that we have two logs with the same base, and we are in fact subtracting here. So since we are subtracting, we can use our quotient rule to rewrite this two logs as one single log of base 6. So log base 6 of, now since it's subtraction, we need to write this as division. 9x over 4 is equal to just a 2. Right? Well, I can't really clean this up like I did in the previous step. So all we're going to do now is we're going to go ahead and convert this. Convert. Convert to exponential form. The reason we're converting is our brain's a little bit, we like thinking about it in terms of exponentials. Our brain handles it a little bit better. So we're going to have 6 raised to the second power is equal to whatever the argument was. Here the argument is in fact a fraction, 9x over 4. Yeah? Well, again, this is just an Algebra 1 problem, something that we can definitely handle at this particular point. So let's go ahead and make our Algebra 1 teacher proud. Well, 3 squared is 36. Is equal to 9x over 4. Now, there's a couple different ways you can solve this, right? 36 equals 9x over 4. You can think about this as a proportion and then do cross multiply, right? We can go ahead and do it that way. Or we could think about this as 36 is equal to 9x over 4 with a fraction and maybe multiply by the reciprocal, both sides by 4 over 9, right? Either way, we will go ahead and be able to get the answer that we're looking for. Either way we do this, we'll get an answer. I believe it's going to be 16, I think is our answer here. X is equal to 16. Either way, okay? Yep, 16. All right, so the second set of problems on our Delta Math are going to be dealing with these log properties. I gave you an even split, 3 of using the product rule and 3 of using the quotient rule as we're going through, right? And then the solving is going to happen from there. The first 6 problems deal with these exponential equations. The next 6 deal with these log equations where we're going to have to utilize the properties and then convert, okay? All right, so let's go ahead and go to the back. I only gave you 2 of some of the harder problems, which at least I consider to be harder problems. And that's where we're going to give you purely exponential problems, and we're just going to convert to exponential form, and we're going to add a little and piece here, but I'm not going to tell us what it is just yet. So these particular problems, you'll note that they are just straight up logs, so they kind of look like the middle step of where we were on the previous problem. So to really kind of make our brain understand these, what we're going to do to start with is we're going to go ahead and convert each of these into exponential form. And we kind of actually already had a little bit of practice with this. One of the earlier Delta Maths I gave you, we were setting up these kind of crazy equations. I told you we were going to come to this at some point. Today is that day. So we're going to go ahead and convert. Remember, the base is the base is the base is the base. So I'm going to have x, and here I'm going to have x plus 6. And if we're converting, we know that the exponent is just what we're equal to. So here it's going to be x squared, and this is going to be x plus 6 squared. And we're just going to set those equal to whatever the arguments were, which in this case was 7x minus 10 and 2x squared plus 3x. Okay, so we're just doing our conversions like we did and we practiced before in an earlier Delta Math. All right, so the question is, what do we do now? Well, technically, these are just problems that we've encountered before way back in Unit 4. These are just quadratics, right? So let's go ahead and kind of clean this thing up a little bit. We'll start with this first one. I'm going to move everything over to the x squared side. So I'm going to start off by subtracting 7x and adding 10, right? Minus 7x and plus 10. So that way I can rewrite this as x squared minus 7x plus 10 is equal to 0. Now, on this other side, it's going to be a little bit more difficult. What does x plus 6 squared actually mean? How do we deal with squaring? What does it mean to square something? Does it mean multiply by 2? No, it means multiply by itself, right? X plus 6 times x plus 6. Well, x plus 6 times x plus 6, that's just a bunch of distributive property. So we're going to get x squared plus 6x plus 6x plus 36 is still equal to that 2x squared plus 3x. I'm going to go ahead and combine like terms here, giving us x squared plus 12x plus 36 equals 2x squared plus 3x. Looking to try to combine like terms like I did before, let's move everything over to the right-hand side here. Now, why would I want to do that? Well, I want to get a positive x squared. So minus 12x, minus 12x, minus 36, minus 36. Just like over here, it went away, giving us x squared minus 9x minus 36 equals 0. I can rewrite the 0 on either side, technically, so I'm going to rewrite it as equal to 0 on that side. Right? Maybe that was too much for everybody. I'll just write equals 0 here. And then rearranging it, we get x squared minus 9x minus 36 equals 0. And there we are. Wait a minute. Well, there we are. We haven't finished this yet. What do we have to do? Well, when we're solving quadratic, what's the first thing we're trying to look to do each time? What's something that we should always try to do, especially when my lead coefficient is 1? We should try to well, we talked about it way back when in unit number 5. Oh, wait, was that? It was this idea of factoring. Remember how we factored quadratics, right? We talked about factoring by grouping. We had this process right here where we went ahead and we made our little chart. We split. We had this little division here. We had this kind of this idea of working through. And then we went ahead and we said, well, you know what? We can kind of condense this down. And we talked about this idea of factoring. We talked about GCF. We had the grouping, or more importantly, these last, the third here and the last one. If a is equal to 1, when we made our chart, our answers just appeared. The values that were inside the parentheses just were the ones that were in the chart. All right. I'm going to go ahead and recopy that other one down a little bit just so we can see. We have x squared minus 7x plus 10 is equal to 0, right? So our goal here is we're going to eventually set them equal to 0, right, in terms of the solving. So notice again, our lead coefficient here is actually going to be 1. So let's go ahead and see if we can factor these. If we remember how to do our factoring, we do a times c, so that's 1 times 10, which is 10. Here we're doing 1 times negative 36, which is negative 36. That's what we're looking for. And our value in the bottom is, in fact, going to be our b value, which in this case is negative 9, and here it's negative 7. So what are two numbers that multiply together to give us 10 but add up to negative 7? And what are two numbers that multiply together to give us negative 36 but add up to negative 9 is our thought in question here. Well, in the first one, we're going to have negative 2 and negative 5 will be our two values. And in this other one, we're going to have negative 12 and positive 3. Well, what does that mean? Well, in terms of factoring, we could go ahead and do the full process, but we should note that that means our answers are just going to be as such. We're going to have x and x, minus 2 and minus 5, and this will become x minus 12 and x plus 3. Remember, we spent a great deal of time talking about how there's the idea of factoring and then solving by factoring. We're not completely done yet because we actually need to solve for these. What are our answers going to be for the first one? If x minus 2 and x minus 5 equals 0, that means my answers are x is equal to 2 and x is equal to 5. Here, then, that means x is equal to 12 and x is equal to -3. So notice we're getting 2 answers for each of these because we ended up actually factoring. Sometimes we need to check these answers. In this particular problem, we are not. We won't have to worry about that just right yet. That's, again, more of an advanced level question when we have to check, but we could obviously easily check in Desmos as well. All right.